Chapter 7 is also on quadratics, and it's on quadratic equations. Section 7.1 is solving quadratic equations by graphing. In this unit, we're going to be solving quadratic equations by graphing, factoring, and by using the quadratic formula. And many times you can solve an equation either one of those ways, but choosing the most efficient way is probably the most important thing when solving a quadratic equation. So a quadratic equation is a polynomial equation of the second degree, and that basically just means that the highest power of x that you have in your equation is an x to the power of 2. So for example, anything that has the form ax squared plus bx plus c equals 0 can be considered a quadratic equation. The roots of an equation are the solutions to an equation. So for example, the equation x squared minus 3x minus 10 equals 0 has roots x equals 5 and x equals negative 2, because if you plug those values in for x in that equation, it makes a true statement. For example, 5, if you plug it back into that equation, 5 squared would be 25, minus 3 times 5 would be 25 minus 15 or 10, and 10 take away 10 would equal 0, so it works. And similarly, negative 2 would work if you plug that value in for x. And so therefore, because they make the equation true, they're considered roots of the equation. If you're solving an equation equal to 0, these roots can also be referred to as zeros, because zeros by definition are values of the variable which make the equation equal to 0. So let's look at how you can find the roots of zeros and how they're related to the graph of an equation. Excuse me. So the first one we're given here, for example, we're given the graph of y equals x squared minus 4x minus 12, and we're asked to determine the vertex. And since the graph is drawn for us there, we can actually determine the vertex by just looking at the graph and see that the vertex is right here, which has coordinates 2, negative 16. Now, if you didn't have the graph in front of you, you could always use from the equation, you could use x equals negative b over 2a to get the x coordinate of the vertex, which in this case would be negative of negative 4, which would be positive 4, because the b value is negative 4, and 2 times the a value is 2 times 1. So that would give you an x coordinate of 2, and if you plug it back into the equation, you would get 2 squared. Y equals 2 squared minus 4 times 2 minus 12, which works out to be 4 minus 8 minus 12, which is negative 16. So algebraically, that's what you would do to find the coordinates of the vertex if you didn't have the graph. Just a little bit of review there. Okay. So the factored form of the equation would be y equals, you'd need x to be in the first term, because x times x will give you the x squared, and you would be looking for two numbers which multiply to give you negative 12, but add to give you negative 4. So the two numbers that multiply to give you negative 12 but add to give you negative 4 would be negative 6 and positive 2. So negative 6 and positive 2. And you can check x times x would give you x squared, x times 2 would give you 2x, and you move to 6 times x would give you minus 6x. So together they would add, negative 6x and the 2x would add to give you negative 4x, and then negative 6 times 2 would give you the negative 12, if you were multiplying that equation out. So the x-intercepts, if you look at the graph, are x equals negative 2 and x equals 6. And the y-intercept from the graph would be y equals negative 12, sorry. And you can also get the y-intercept from the equation by plugging 0 into the equation. So it says, how can you use your graph to solve x squared minus 4x minus 12 equals 0? Well, if we look at the equation that we have, the only difference between this equation that we're given the graph of and this equation that we're asked to solve is that this has y and this has 0. So if we're going to look at the graph of this equation, we're particularly interested in where the y is 0. You need the x values. Which make the value of the equation equal to 0. And that would be the x-intercepts. Because every x-intercept on the graph would have a y-coordinate of 0. So x from the graph, the solutions to that equation should be the same as the x-intercepts, which are x is equal to -2 and x is equal to 6. And if we plug those into the equation, we would find that they would actually equal 0. Right, the second example says to graph y equals x minus 2 all squared by using your knowledge from the previous unit. So we know the vertex in this graph. The equation is written in the vertex form of the equation, which is a outside of x minus h all squared plus k, because all the x's are part of the squared term. So the vertex would be hk. So in this case, the vertex would be 2 and 0, because there is no k value. The x-intercepts, if we use our knowledge from the previous chapter, when we're solving the x-intercepts, we're letting y equal 0 in your equation. So that would be 0 equals x minus 2 times x minus 2, because that's what x minus 2 squared means. So therefore, x minus 2 equals 0, or x minus 2 equals 0, which is the exact same thing. So you end up basically with one solution there of x equals 2, because both of those things would yield x equals 2. And the y-intercept, you would let x be 0. So that will give you y equals 0, take away 2, all squared. You're just putting 0 in for x in the equation, which is going to give you -2 squared, or 4. So this is how could you use the graph to solve. Oh, we've got to graph it first, sorry. So we're going to graph, our vertex would be 2, 0. Our y-intercept would be about 4. So that would be there. So now using symmetry, we know that there should be another point 1 unit to the right of the axis of symmetry at a height of 4 as well. And our graphs, just a rough sketch of the graph, would look like this. Now we can also plot another couple of points, like we can plug in another value of x if we want. For example, x equal to 6 would give you 6 take away 2, which is 4 squared, would be 16. So that would be up here somewhere if we plugged it in. And there should be another one on the other side at -2 at a height of 16 as well. So you could plot some more points if you didn't think that was enough. So it says, how could you use the graph to solve x minus 2 all squared equals 0? Again, we've got the graph of y equals that, so we'll be looking for the x-intercept, because y equals 0 would mean that it would be the x on the x-axis, or the x-intercept. So the x-intercept. So x equals 2 should be the answer. It said you should notice that solving quadratic equations above is the same as finding the x-intercepts, because this example and the one previous had basically the x-intercepts were the same as setting that equation equal to 0, looking at the factor form of the equation and setting each of the factors equal to 0. So if you want to check your answers to see if you are right, if your guess or your x-intercepts, if you did it correctly, you can always take your answers and sub them back into the original equation to see if they make the equation work. Right, so the next example says solve using each equation by using the graph provided. So if we look at what you're asked to solve and look at the equation that's provided, those two parts are exactly the same. So we would be looking for where the y is 0, which means the solutions would be the x-intercepts. So x equals, this one here looks like it's about, it's a little bit more than a half, so we can negative a half, so probably -0.7 approximately. and this here would be the other value where the y coordinate is 0, which would be x equals positive 1. The second example has the equation that you're asked to solve equal to 0 is exactly the same equation that you're asked to, that you're given the graph of. So you've got the graph of y equals to negative 2x squared plus 5x equals, negative 2x squared plus 5x plus 3 is the equation that you're graphed, and you're looking for y equals that, and you want specifically where the y is 0. So that would again be the x-intercepts. So that would be x equals negative, that looks like around negative 0.5 approximately, and x equals, the other one would be here, which is x equals 3. Example 3 says a pass of a football at one particular kickoff can be modeled using the function h of d equals negative 0.02d squared plus 2.6d minus 66.5, where h is the height of the ball above the ground in yards, and d is the horizontal distance from the kicking team's goal line. So the graph is provided below, so you can see that the ball was kicked at around probably 35 yards, I guess, and it was kicked up into the air and then came back down again to the ground. So it says, what are the x-intercepts? So the x-intercept in this case seems to be around 35 yards. And x equals around 95 yards. So this is, what do they mean in the context of this problem? So in this case here, this is the 35 yards is where the ball started. And this here is the ball landed at the 95-yard line. So the ball landed at the 95-yard line. And it says, why are there two x-intercepts? Well, there's two x-intercepts because the ball reaches a height of 0 at the beginning and then when it hits the ground again. There are two x-intercepts since the ball starts on the ground, height 0, right? Whoops, ground. Starts on the ground. Which is height equals 0. And ends and lands on the ground. Which is height equals 0 again. So there's two places where the height is 0. So why is the y-intercept not labeled on this graph? Well, if you were to extend this graph to where it crosses the y-axis, it would actually not cross over till you get into the negatives. So if the graph was extended, to touch the y-axis, it would have a negative y-intercept. Which would mean, in this case, the ball is below the ground. Which doesn't make sense. Okay, so that's why it's not labeled on the graph. So what horizontal distance does the ball travel before it hits the ground? So if you look at, it started at the 35-yard line and it ended at the 95th yard line. So that'd be 95 minus 35 equals 60 yards. Example 4, how can you determine the zeros? So the zeros, by definition, are the values of x that make an equation equal to 0. So if you're looking for the zeros, you would be basically taking this and changing it to a 0, which if that's equal to 0, and you're looking at the graph of this, and this is exactly the same equation, you want x squared plus 6x plus 8 equal to 0, and this is x squared plus 6x plus 8 equals f of x. So this graph shows all the possible values of x squared plus 6x plus 8. We are interested, if we're looking for the zeros, we are interested in where this is 0, which means you'd want the x-intercepts would be the values of x that make the equation equal 0. So this would be, in this case, the zeros would be x equals negative 4 and x equals negative 2. And if you plug those back into the equation, you would find that they make the equation, both make the equation equal 0. Alright, so the roots of an equation, ax squared plus bx plus c equals 0, are the values of the variable x that make an equation true. Since this equation is equal to 0, these roots can also be referred to as the zeros of the function of the equation. The roots or zeros of the equation are the x-intercepts. So if you're solving an equation equal to 0, the roots or zeros of that equation would be the x-intercepts of the graph of the corresponding function y equals ax squared plus bx plus c. It's important that these two parts are the same. So two students provided solutions to the equation x squared plus 5x equals 24 using graphing. Each solution is shown below. Are both solutions correct? And you have to explain. So the first student says the x-intercepts of the graph of y equals x squared plus 5x minus 24 shown below will be the solutions for x squared plus 5x equals 24. And if we look at that, that would actually be true, because when you're looking at the graph of this, you want to have the same equation here, and you want to have the equation equal 0. So you rewrite this equation right here as x squared plus 5x minus 24 equal to 0. Then you would actually be looking for the x-intercepts of this graph right here, because this here matches this. So by bringing that 24 over, we basically have an expression x squared plus 5x minus 24. So if we graph the equation y equals that expression, we would be actually looking for the x-intercepts of that equation to solve x squared plus 5x minus 24 equal to 0. So the x-intercepts should be the solutions, and you can check to see if they're both solutions. So we check x equals negative 8, for example. You get negative 8 squared plus 5 times the negative 8 minus 24. So that's the left side of the equation. And that gives you 64 minus 40 minus 24, which is 0. So that's a solution. And then if we check x equals 3, we can see that the left side is equal to 3 squared plus 5 times 3 minus 24, which is 9 plus 15 minus 24, which is again equal to 0, which equals the right side of the equation. So therefore, that's a true solution as well, or root. So that student would be correct. If we look at the second example, the second student said the graphs of y equals x squared plus 5x and y equals 24 can be drawn. So what they did is they kept basically the equation, they split up the equation x squared plus 5x equal to 24 into two separate equations. They graphed y equals x squared plus 5x, and they graphed y equals 24. And then when you graph this one here would be y equals x squared plus 5x, the parabola, and this would be y equals 24. So when you graph those equal to each other, where y is 24 would be right here, and the x that makes it 24 would be x equals -8 and x equals 3. So you'd be looking for the x coordinates of those points. And if you check again into the equation, x squared plus 5x equal 24, if you check x equals -8, you would get -8 squared plus 5 times -8 is 64 minus 40, which equals 24, which equals the right-hand side of the equation. So that works. And then if you check x equals 3, in the equation, you get 3 squared plus 5 times 3, and that's 9 plus 15, which is 24, which is the right side of the equation, so that one works. So both students' solutions are correct. All right, example 6, you're asked to solve this one by graphing, and this one here, you would use technology. To graph. So I'm going to omit that one because, well, first I'll just tell you what you'd have to do. You'd have to first expand this. 4x squared plus 12x equals 12x plus 9. And then you'd want an equation equal to 0 so that you could look at the graph's x-intercepts. So you would bring all terms to one side. And you would get 4x squared minus 9 equals 0. So you would graph, using technology, y equals 4x squared minus 9, and determine the x-intercepts. Now you could, if you want, you know enough about this from the last chapter, you could actually, you would know that this graph would cross over the x-axis. Would have a vertex. This is in vertex form, a vertex of 0, -9. And then if you just pick some points and plug them in, for example, x equals 1 would go with 4 times 1 squared minus 9, which would be 4 minus 9, or -5. So x equals 1 would go with -5. And by symmetry, this one here on the other side of the axis of symmetry would go with -5 as well. Then if I check, for example, x is 2, it would be a lot easier if you had technology. But I can't show you the technology, so I'm just going to do a rough sketch. And that would give you 4 times 2 squared minus 9, which is 4 times 4 is 16, minus 9, which is going to be 7. So 2 goes with 7. And then, so one more unit over from our last point, -2, would also go up with 7 because it's symmetrical. Axis symmetry would be at x equals 0, so 2 on the other side of the axis symmetry would be up as high as 7 as well. So there's your graph. It's hard to get it through all those points there. So your 2 points of intersection, I'm a little bit off on my graph on this side right here, crossing over. So it looks like the graph is crossing over at around x is approximately, 2 x-intercepts are approximately -1.5 and approximately 1.5 it looks on that graph. Mine's a little bit off, but halfway between, or partway between -1 and -2, and partway between 1 and 2. And you can use technology to verify that if you like. You can see by graphing by hand is a little bit of a pain in the butt because you can't always see exactly where it's crossing over the x-axis. So it says, look back at the examples we've done previously. Are the x-intercepts of a quadratic function always integers? And the answer to that would be no. Does every quadratic function have to have 2 x-intercepts? And we saw that in our example set, there was some that only have 1 x-intercept. So that answer to that question would be no as well. There's also possibility, that the graph wouldn't have any x-intercepts if you had something like that. So the vertex, if you look at the table below here now, they're just giving you some situations and asking you to determine the number of x-intercepts if you know the vertex and the direction of opening. So the first one here, if you had just a rough sketch now, the vertex would have a +2 and a -3 vertex, so it's somewhere around here in the 4th quadrant, but it would open up. So this would obviously cross over the x-axis in 2 spots. So there'd be 2 x-intercepts. If you had vertex of 1, 2, 3, 4, 5, 0, and it opens down, then it would only be touching the x-axis right at that vertex, which would be 1 x-intercept. Should be labeling my x and y axis. We're just giving it a little rough sketch, so it's not a big deal if I have it labeled perfectly. Okay, and the next last one would be vertex of 4, -2, so 1, 2, 3, 4, and then down 1, 2. So it'll be down here again, but opening downward this time. This would be your x-axis, this would be your y. So if it's opening down, it would have no x-intercepts. So if you know the vertex, you can see from that, and direction of opening, you can determine how many times it crosses the x-axis. That would well how many solutions to that equation equal to 0 if you were solving it. Okay, so the last bit here now is just a little bit of putting that kind of knowledge together and saying if the graph of y equals ax squared plus bx plus c is being used to help solve the equation ax squared plus bx plus c equals 0, and the graph has no x-intercept, what does it tell you? What does this tell you about the solutions to the equation ax squared plus bx plus c equals 0? So if you were to graph, for example, just draw sample here, and it had no x-intercept, so something like this could be an example of y equals ax squared plus bx plus c, and there's no x-intercepts, so that would mean that this equation equal to 0 would have no real solutions. Because there are no values. If this equation here represents all the possible y values of that expression ax squared plus bx plus c, then if all the y values are greater than or equal to 0, and there are none that are equal to 0, therefore this equation would have no solutions, or no real solutions at least. So there's some questions there on and a worksheet on graphing equations that you can get from me to practice these topics.